Okay, let's dive straight into something that might just make you tilt your head and go, huh.
Okay.
Imagine our universe is shaped like a giant cosmic donut.
Right. And that's just a taste of the kind of wonderfully unconventional thinking we're plunging into today.
All right, I'm intrigued already.
We're taking a journey, you and I, into the realm of outsider physics, inspired by the book Physics on the Fringe.
Ah, outsider physics. So people thinking about the universe outside the usual academic channels.
Exactly. Forget the usual lectures. We're exploring theories cooked up by individuals fueled by, well, just pure curiosity. People who might run a trailer park.
Okay.
Craft the soundscapes for huge Hollywood movies.
Wow.
Or even, well, we'll get to the tanks later.
Tanks. Okay, now you really have my attention.
Buckle up, because we're about to meet some truly original minds. But before we get too deep into this, quick reminder to our awesome listeners, hit that like button and subscribe to the channel to support the show and all our deep dives into the unknown.
It's the cosmic fuel that keeps these explorations going. And what's immediately striking, is that these are individuals deeply compelled to understand the universe.
Often without the formal training we typically associate with scientific inquiry.
Yeah, no PhDs required for this deep dive.
They're looking at the same cosmos, asking similar fundamental questions, but their approaches and the frameworks they build can be dramatically different.
Totally different paths.
It makes you wonder about the diverse ways people arrive at knowledge, and the role individual perspective plays in shaping how we see reality.
Absolutely. And we're not talking about folks who've just decided the sky is green for kicks. These are people who've genuinely grappled with established science and thought, hang on, there might be another way to look at this.
A different angle.
Take Jim Carter, trailer park owner. He looked at Einstein and Hawking and basically said, hold my beer and my entire alternative description of the universe.
Huh? That's quite the statement.
Then there's Walter Murch, Oscar-winning sound designer. He spotted this hidden mathematical rhythm, he thought, in the distances between planets and moons.
The film guy. That's fascinating, from soundscapes to celestial mechanics.
Right. And Roto.
Yeah.
Well, Roto pictures our entire existence happening inside a colossal torus, a donut.
Back to the donut. Intrigued. I am beyond intrigued. Our mission today is basically to unpack their core ideas.
Understand where they're coming from.
Yeah, explore what drove them, their unique perspectives, and maybe even gain a fresh appreciation for the sheer human drive to figure this whole cosmos thing out.
And as we delve into these alternative viewpoints, it's really crucial we keep an open mind.
Absolutely. No judgment here.
Our aim isn't to debunk or validate, right? It's to understand these theories on their own terms.
What are they really saying?
What are the fundamental assumptions? What observations or maybe intuitions are they built on?
Yeah.
And ultimately, what can we learn from the very existence and, frankly, the dedicated pursuit of these unconventional ideas? What does it tell us about scientific thinking itself?
Great point. Okay, let's kick things off with Jim Carter, the trailer park owner who decided to, write his own version of reality.
The one who challenged Einstein and Hawking? That's the one. Back in 1993, he put out The Other Theory of Physics, and this book promised a complete overhaul.
Not just a minor tweak.
No way. He aimed to solve some of the biggest puzzles, the moon's origin, gravity, the very fabric of space-time, all through his concept of Circlon Synchronicity.
Circlon Synchronicity. Okay.
And this wasn't just like adding a footnote to existing physics. This was a ground-up redesign, a replacement.
What's fascinating about Carter, though, is the sheer scope of his ambition.
It's huge.
He wasn't content tackling just one niche problem. He wanted a holistic explanation for everything.
The whole enchilada.
And his background is key here, isn't it? Self-taught mechanic.
Yep, fixing up old Chryslers and Cadillacs, lots of hands-on work.
Exactly. And that practical mechanical intuition, you can see how it deeply informed his theoretical approach.
Definitely. It kind of highlights how our personal experiences, the way we interact with the physical world, can shape even our most abstract ideas about the universe.
It really does.
So from this mechanical mindset, he develops his fieldless universal Circlon theory, or FUCT.
Okay, the acronym. He must have had a sense of humor.
Oh, I think so. The central idea. Everything, and I mean everything, is built from fundamental, springy, Circlon-shaped particles.
Circlons, so donut-shaped again, or ring-shaped.
Kind of ring or tube-shaped, yeah, toroids.
Yeah.
And all matter, all energy, all physical phenomena emerge just from the geometry and motion of these circlons.
So no fields, like electromagnetic fields, gravity fields, none of that.
Nope. Fieldless. As he put it, very directly, there is nothing in the entire universe which is not made of circlons.
Wow. That is a bold claim. It's a very fundamental particle-based view.
Right.
Almost takes you back to earlier scientific models, doesn't it? Before our modern understanding of fields really took hold.
Yeah, like before Maxwell or Einstein, really.
Instead of abstract concepts like electromagnetic fields, those invisible regions of influence around charges or gravitational fields, the warping of space-time.
Which are hard to visualize sometimes.
Right. Carter posits a concrete building block, a physical thing. It reflects this deep human intuition, I think, to understand the universe in terms of tangible bits and pieces, things working like machines.
And this wasn't just some flash of inspiration he had one afternoon.
No, he'd been working on this for ages, apparently.
Decades. His earlier work, The Cosmic Ring, came out way back in 1974.
74.
And it already laid out a very different picture of reality, directly challenging the foundations of mainstream physics.
And what was that book like, physically?
Oh, picture this. 144 pages, held together with staples, filled with hand-pasted diagrams, equations meticulously written out by hand.
Wow, like a scientific zine or something, a manifesto made in a garage, like you said.
Totally. The sheer physicality of it speaks volumes about his dedication, his personal commitment to this vision.
Absolutely. The Cosmic Ring sounds like a testament to a highly personal, handcrafted view of the universe.
And within that vision, these fundamental circlons, they weren't just microscopic things.
No, he saw them bigger.
Oh, yeah. Carter saw their manifestations across all scales, from tiny bubblons and underwater bubbles to worlons, making up the Earth's magnetic field.
Worlons for the world, got it.
Solons, causing solar prominences on the sun.
Solons for the sun.
And even the huge giant ring nebula out in the constellation Lyra.
So that giant gas ring in space is circlons too.
In his view, yes. All different expressions of this one fundamental circlon form. It's this fascinating attempt to find a single unifying principle across vastly different stuff.
Bubbles, magnetic fields, stars, nebulae, all circlons. That's comprehensive.
Right. And when it came down to the nitty-gritty, the stuff we're actually made of, Carter envisioned the basic units, protons, neutrons, electrons, mesons, as hollow tubes, toroids again, the different sizes for each particle.
So forget quarks and leptons from the standard model.
Yeah, his fundamental particles were these neat little tubes, elegant almost.
And how did he picture atomic nuclei, putting these tubes together?
Exactly. His model had these circlon-shaped particles interlocking, forming a kind of subatomic mesh. And he believed this mesh structure actually mirrored the patterns in the periodic table of elements.
Whoa, really? He connected it to the periodic table?
Yeah, he even created these incredibly detailed diagrams showing how he thought copper and uranium nuclei were built from these interlocking circlons.
That's amazing. The sheer visual complexity and trying to link it directly to observed chemistry, that's quite something.
It's a very architectural approach, isn't it? Almost artistic.
It is. Seeing fundamental particles as building blocks assembling according to specific geometric rules, it really resonates with that mechanical background you mentioned.
Yeah, the idea that every part has a defined place and function within the overall design. Like fixing a complex engine.
Precisely.
Now, okay, what about gravity? That's always the big one. How did circlons explain gravity?
Good question. Did he have a mechanism?
He saw his theory as a kind of mirror image to Einstein's general relativity.
A mirror image? How so?
Well, Einstein, as we know, described gravity not as a force pulling things, but as a curvature, a warping of space-time caused by mass and energy.
Right. Mass tells space-time how to curve. Space-time tells mass how to move.
Carter, though, he flipped it. He insisted that space itself is absolute, fixed. It doesn't curve. But matter and time change proportions near mass.
So rulers shrink and clocks slow down near heady objects, but space itself is flat.
That was his take. He famously asked, something changes. Is it matter or is it space? And he felt mainstream physics had just gotten the answer backward.
Huh. That's a fundamental disagreement right there.
And he didn't just leave it theoretical. He actually proposed an experiment to test his idea.
Oh, yeah. What was it?
Taking a ball bearing and a metal tube up on the space shuttle to observe how they interact in microgravity away from Earth's influence.
To see if their dimensions or their interaction changed in a way his theory predicted versus Einstein's.
Exactly. It highlights a crucial aspect of his method. He wasn't just throwing out abstract concepts. He was thinking about potential experimental tests, however unconventional they might seem.
That's important, even if his interpretation of potential results might differ wildly from mainstream expectations, that desire to connect theory with observable stuff, that's a core part of scientific thinking.
Definitely. Then, much later, in 2011, came his book, The Living Universe.
The living universe, okay.
And this introduced another radical idea, an evolving universe, but not expanding like in the Big Bang model.
How is it evolving then?
It was driven, he thought, by a single constant of nature that was actually changing over vast cosmic timescales.
A constant that isn't constant. What's one?
Specifically, he proposed the mass of the electron was slowly decreasing over billions of years.
The electron's mass is changing. Wow. Okay, what would the consequences of that be?
Well, according to Carter, this could explain everything from the size of atoms, the Bohr radius,
Right, which depends on electron mass.
to the fine structure constant, another fundamental number in physics.
Also involves electron properties.
And even the redshift of light from distant galaxies.
Wait, redshift? He explained cosmological redshift without an expanding universe.
That was his claim. The decreasing electron mass over cosmic time would cause atomic energy levels to shift, which would affect the light emitted way back when, making it look redshifted by the time it reaches us. No expansion needed.
That's a completely different explanation for a cornerstone piece of evidence for the Big Bang.
Totally. And he even proposed a whole alternative cosmology to go with it, a matter bifurcation process.
Matter bifurcation.
Yeah, starting from a single antineutron God particle.
A God particle. Okay.
Which then decayed or transformed into neutrons, which then decayed into the hydrogen atoms we see filling the universe today, all while carefully maintaining the conservation of mass throughout the whole process.
So a whole different origin story for matter itself, stemming from his evolving electron idea.
Exactly. It's a complete alternative picture. The concept of fundamental constants maybe changing over time is a huge departure from the standard model, which assumes they are, well, constant.
It really is. His matter bifurcation idea, it's another testament to his persistent drive to create this totally self-consistent, alternative picture of reality, all built on his Circlon framework.
And if you thought his intellectual curiosity stopped at physics, think again. Back in 1988, Jim wrote a pamphlet called The Four Sexes.
Like human relations.
Exactly, outlining a theory of human relations based on four fundamental sexual types. Yin and yang, but for both men and women.
4 types. So male yin, female yin, female yang.
Precisely. He saw symmetry and complementarity as key principles here, just like in his physics. Yang was outwardly directed, yin was inwardly focused, distinct tendencies, preferences for each type.
So he's applying these fundamental symmetry ideas from his physics to psychology or sociology.
Seems like it. He even proposed, quote, many experiments that could be done to test his theory. Though he also noted that most people he showed it to could readily identify themselves and others within his 4 categories.
It's remarkable, isn't it? This recurring theme of symmetry, complementary pairs, showing up not just in his physics, but also in his theories about people.
It really is. That drive to find these grand overarching principles that explain totally different parts of reality, that's characteristic of a lot of big thinkers, both inside and outside the mainstream.
It certainly is.
But beyond the theories themselves, you have to talk about the look of his work. Jim's books, his collages, the models he built, hundreds of illustrations, both hand-drawn and computer-generated. They have this truly unique artistic flair.
Right. You mentioned diagrams before. He was very visual.
Extremely. So much so that his work was actually exhibited at the Santa Monica Museum of Art back in 2003.
An art museum exhibition for his physics diagrams and models.
Yeah. He wasn't just writing about his Circlon universe, he was actively visualizing it, creating these tangible representations of his ideas.
That artistic dimension sounds like it was totally integral to his whole project.
I think so.
The visuals weren't just like helpful additions. They were a fundamental part of the theory itself, a way to grasp and communicate his concepts that went beyond just math or words.
And then there were the smoke ring experiments.
Smoke rings. What was he doing with smoke rings?
Using everything. Soda bottles, cigarettes, apparently a massive oil storage tank at one point, even garbage cans.
What? Why?
All in an effort to understand the dynamics, the behavior of vortex rings, which he saw as analogous to his theoretical circlons.
Ah, so the smoke ring was like a large-scale model of a circlon's behavior.
Exactly. He viewed theoretical physics as a kind of gold mining. You had to put in persistent effort, try different things to uncover valuable insights.
That's a great analogy. And it's interesting, too, because his fascination with smoke rings It actually connects him back to some 19th century physicists.
Oh, yeah.
People like Peter Guthrie Tate and William Thomson Lord Kelvin. They also studied vortex rings extensively.
No way.
Yeah. They even speculated for a while that stable vortex rings in the ether might be the fundamental constituents of atoms and matter.
Seriously. So Carter was unknowingly echoing Kelvin.
In a way, yes. It's a fascinating historical echo. Shows how certain physical analogies, like the smoke ring, can capture the imagination across different eras.
That's wild.
So for Carter, the smoke ring served as this tangible, observable thing, both an analogy and a source of inspiration for his abstract Circlon theory.
And later on, he even started using 3D animation software to visualize Circlon dynamics.
Really? Bringing it into the computer age.
Yeah, further underscoring his commitment to making his ideas concrete, understandable, at least within his own framework, trying to show how these circlons would move and interact.
Quite a journey, from hand-stapled books to 3D animations.
Absolutely. All right, let's shift gears now. Let's delve into the world of Walter Murch.
Ah, the film guy.
The film guy. A name that might ring a bell if you're a movie buff. Legendary Hollywood film editor, sound designer.
Apocalypse Now, The Conversation, the Godfather films. I mean, his work is iconic. A genius in cinema sound and editing.
Totally. But this Oscar-winning creative force also harbors this deep interest in physics, specifically an intriguing extension of a rather old idea, Bode's law.
Bode's law, right. Titius Bode law. That's the 18th century thing, isn't it?
That's the one. An empirical observation, basically, that suggested the distances of planets from the sun followed a simple mathematical pattern.
Yeah, roughly like each planet is about twice as far out as the previous one. With some adjustments, a simple numerical sequence.
Exactly. And originally, it seemed to work pretty well for the known planets back then.
And didn't it help predict where Ceres would be found? In the asteroid belt?
It did. That was a big success for the law. But then Neptune was discovered.
Ah, Neptune, the rule breaker.
Big time. Its orbit didn't fit the formula at all. Pluto was kind of ambiguous. It landed roughly where Bode's law predicted Neptune should be.
Right, so because of Neptune, mostly, mainstream astronomers have largely dismissed Bode's law. They tend to see it as just a numerical coincidence, a fluke.
Which is understandable. But this is where Walter Murch enters the picture.
Okay, so what did Murch do with it?
Since around 1995, he has been meticulously compiling data, looking at planetary systems, moon systems.
They're going beyond just the sun's planets.
Way beyond. He argues Bode's law isn't just a random fluke. He thinks it reflects some fundamental underlying principle governing how these systems form and stabilize.
A deeper architectural rule.
That's the idea. And he's extended the law, applying it not just to planets orbiting the sun, but also to the distances of moons orbiting their planets. Jupiter's moons, Saturn's moons.
Okay, applying the same pattern to moon systems.
And even to the orbital distances of extrasolar planets orbiting other stars.
Whoa, exoplanets too. He thinks Bode's law works out there.
He's collected data suggesting it does, or at least that similar logarithmic spacing patterns appear frequently.
That's ambitious, taking this old, somewhat discredited law and applying it universally.
And he hasn't just kept these findings to himself in a notebook. He's presented his research.
Oh, really?
At institutions like Occidental College. And apparently these weren't like hand-wavy talks.
No.
No, they were incredibly professional PowerPoint presentations, packed with diagrams, graphs, detailed data tables, really systematic.
So he's engaging with the scientific community, presenting evidence.
By all accounts, yes. Impressive displays of independent scientific investigation. He systematically laid out his evidence and really tried to address the skepticism from mainstream astronomers.
The sheer professionalism is noteworthy, isn't it?
Yeah,
especially coming from someone whose main career is so different.
Absolutely.
It shows this serious engagement with the standards of scientific discourse, even if his conclusions are outside the prevailing consensus.
Right. He's presenting data, analysis, trying to support his claims. That's the core of scientific argument.
The debate, of course, then becomes whether that data is compelling enough. Is it statistically significant? Does it really warrant reviving Bode's law as something more than just a historical curiosity or a coincidence?
That's the million-dollar question, isn't it? But fascinating that someone like Murch is pursuing it so rigorously.
Definitely.
Okay, now for something truly toroidal.
Back to the donuts.
Back to the donuts. Let's talk about Roto, author of the wonderfully titled book, Kinematics, The Reinstatement of Common Sense.
Ether kinematics. Okay, breaking that down. Ether motion.
Pretty much.
Yeah.
Roto's central idea is that Our universe isn't expanding. It's not doing any of those complicated cosmological things. Instead,
Let me guess.
it's shaped like a colossal donut, a torus.
Called it.
And this shape arises from the dynamic motions of an all-pervading ether.
Ah, the ether. So he's bringing that back.
He is. Ether theories, as you know, are a whole class of alternative physics.
Yeah, they were dominant before Einstein, really. The idea that light waves, for instance, needed something to wave through, like sound waves need air, this invisible medium filling all of space.
Right, and it's interesting. Jim Carter, Mr. Circlon, he explicitly distinguished his theory from ether theories. He didn't want his circlons thought of as ether particles.
So even within the fringe, there are distinctions and disagreements. Not one unified block.
Definitely not. Now, Roto's personal background is certainly eventful.
Oh, yeah. You mentioned tanks earlier.
Right. According to his bio, he once led a group of civilians on this harrowing 25-mile trek, crawling and walking right past armed Russian tanks in the dead of night.
Whoa. That takes some serious nerve and conviction.
Doesn't it? It definitely suggests someone with unwavering belief. And get this, in the year 2000, the website Net Profit awarded him the Nobel Prize for exceptional contributions to truth.
The Nobel Prize, spelled Nobel.
That's the one. You really can't make this stuff up.
Wow. Okay. So his etherokinematics, the subtitle, The Reinstatement of Common Sense. What does that tell us?
It reflects this desire, I think, for a more intuitive explanation of the universe. Maybe less mathematically abstract than modern cosmology.
Trying to get back to something that feels more grounded, perhaps.
Yeah. And the idea of a universe shaped like a donut, while definitely not standard cosmology, it does provide a specific, relatively simple geometric shape to visualize.
It's concrete, in a way.
Yeah.
Unlike, say, 11-dimensional spacetime.
Right.
Interesting. So we have Carter with his fieldless circlons, Murch reviving Bode's law, and Roto with his ether donut universe. Quite a spectrum already.
It really is. Now, to get some historical perspective on all this fascinatingly fringe science, we really need to talk about Augustus De Morgan.
Ah, De Morgan, the 19th century mathematician.
Exactly. A brilliant English mathematician who developed this keen interest in these oddball outsiders of science in his own time.
And he collected their work, didn't he?
He did. He amassed this huge collection of alternative scientific theorizing. Pamphlets, books, manuscripts, and it was all published after his death in 1872 under the marvelous title, A Budget of Paradoxes.
A Budget of Paradoxes. I love that title. And budget back then just meant like a collection or an assortment, right?
Yep, just a bundle or a bag of stuff. And he used paradox in its older sense, too, not meaning self-contradictory, but ideas that were simply apart from general opinion, outside the mainstream.
So his paradoxers were just people thinking differently.
That was his view. He saw them not necessarily as charlatans or fools, but as people holding perspectives outside the accepted scientific understanding of the day. He approached it almost like an anthropologist.
Oh, so?
He saw himself as a kind of naturalist in the field, studying the characteristics of these discoverers, as he sometimes called them, as a group.
Analyzing the phenomenon of the outsider scientist.
Exactly. He even used this vivid analogy, comparing them to flies buzzing around the giant elephant of mainstream science. They're attracted to it, they interact with it, but they're definitely separate from it.
That's a great image. And what did he think motivated them? Were they just cranks?
He thought their primary motivation usually wasn't to deceive or hoax people. It stemmed more from what he called an excess of integrity.
An excess of integrity. Meaning?
Meaning they had this profound, unwavering belief in their own ideas. Their fundamental flaw, according to De Morgan, wasn't dishonesty, but often an overestimation of the certainty of their own convictions. They were too sure they were right.
Ah, so sincerity, but perhaps lacking perspective or sufficient evidence.
That seems to be his take, and De Morgan's own position in the scientific world probably influenced his somewhat sympathetic view.
How so? Was he an outsider himself?
Well, despite being a really significant mathematician, he made major contributions to logic. He worked at University College London, which was seen as kind of second tier compared to Oxford or Cambridge back then.
Okay.
And he was often critical of the Royal Society, the big established scientific organization. He resigned his fellowship there over a matter of principle.
Ah, so he likely had a personal understanding of what it felt like to propose maybe unconventional ideas or to butt heads with the scientific establishment.
Probably gave him some empathy for his paradoxers.
Makes sense.
And, this period, the mid to late 19th century, was such a time of intense intellectual ferment. Questioning established norms, it even seeped into popular culture.
How do you mean?
Think about Lewis Carroll's Alice's Adventures in Wonderland and Through the Looking Glass, published around then.
Right, Alice.
Carroll, whose real name was Charles Dodgson, was a mathematician himself, a contemporary of De Morgan. He was keenly aware of all these shifts in logic, mathematics, science.
And the Alice books, with their bizarre logic and shifting realities.
Exactly. They can be seen, in part, as reflecting this era's questioning of fixed realities, fixed categories, the kind of stuff De Morgan's paradoxers were also challenging in their own ways.
That's a fascinating connection. Right. Literature reflecting the scientific and philosophical currents of the time.
Definitely. But De Morgan also noted that while mainstream science was making huge leaps, then thermodynamics, electromagnetism, spectroscopy.
A golden age for physics.
Right. Many of his discoverers seemed largely disconnected from these big advancements. They were often pursuing their own kind of isolated, idiosyncratic visions of how the universe worked, sometimes based on much older ideas.
Still trying to square the circle or invent perpetual motion, perhaps, while Maxwell was writing down his equations for light.
Pretty much exactly that in some cases.
Okay, so fast forward to our time. Is this Wild West of scientific speculation still happening?
Oh, absolutely. It's very much alive and kicking. You have organizations now like the Natural Philosophy Alliance, the NPA.
Natural Philosophy Alliance. Okay.
It serves as a contemporary gathering place for what they often call dissident physicists, people who fundamentally disagree with mainstream theories.
A community for the outsiders.
Sort of. And one member, a guy named De Hilster, even compiled a world science database, trying to categorize all these alternative theories.
Taxonomy of the Fringe.
Basically, categories like ether theories, anti-gravity, expanding Earth models, and guess who's in there?
Let me guess.
Jim Carter.
Bingo. Classified under gravity, nuclear structure, and toroidal ring theories. As of 2011, when the book Physics on the Fringe was written, this database listed over 1,900 such dissident theorists.
1,900, wow. That's a lot more than I would have guessed.
Right. It really underscores this enduring human desire to grapple with fundamental physics, often completely outside the boundaries of mainstream academia.
And what's the common thread among these groups, like the MPA? What unites them, besides disagreeing with the mainstream?
Often it's a core belief that contemporary physics and cosmology have just gone drastically wrong somewhere.
Taken a wrong turn. Yeah. They often criticize what they see as overly complex, irrational, or unrealistic doctrines, things like relativity, quantum mechanics, the Big Bang, and there's often a desire for a more accessible science, something understandable without needing years of advanced mathematics. Back to common sense, like Roto's subtitle.
A yearning for intuitive explanations again.
Seems like it. But it's interesting, within the NPA itself, there's often this tension.
Between who?
Between the fiercely independent nature of the individual theorists, each one often completely convinced their own unique theory is the right one.
Right, like Carter versus the ether theorists.
Exactly. Tension between that individualism and the desire to actually form a cohesive community to present a united front against the mainstream. It's a fascinating dynamic.
I can imagine. Everyone thinks they've got the answer, but the answers are all different. Makes collaboration tricky.
Very. And interestingly, even NASA briefly dipped its toes into these waters.
NASA? Really?
Through its Breakthrough Propulsion Physics project, the BPKP, it ran for a few years, ending in the early 2000s.
Breakthrough propulsion. So, like warp drives and stuff?
Kind of. The program was set up explicitly to investigate some of these really way-out ideas for interstellar travel, concepts that were far beyond current engineering, potentially requiring new physics.
What kind of ideas did they look at?
Things like extracting energy from the quantum vacuum, the supposedly empty space teeming with virtual particles, or manipulating space-time itself. They were open to considering ideas that sounded like science fiction.
Energy from empty space. That's a common theme in some alternative circles.
It is. They even had theoretical designs or maybe thought experiments for something called the Gedanken spacecraft.
Gedanken, German for thought.
Right. A thought experiment spacecraft, conceptually powered by interacting with the very fabric of empty space, maybe the quantum vacuum or space-time itself.
Wow. So even a mainstream organization like NASA saw some potential, or at least curiosity value, in exploring the fringes.
For a time, yes. The BPPP initiative, though it didn't last, it signaled this recognition, even within a major scientific institution, that maybe, just maybe, revolutionary breakthroughs could originate from unexpected, unconventional places.
But the challenge always comes back to rigor, doesn't it?
How so?
Well, the significant hurdle for many of these outsider theories is often the lack of rigorous mathematical formalization. And crucially, the lack of clear, testable predictions that can be empirically verified or falsified. Those are really the hallmarks of mainstream physics.
Good point. It's one thing to have a compelling idea, another to turn it into a predictive, testable scientific theory.
Exactly. Which brings us to a really fascinating contrast.
Between the outsiders and the mainstream.
Yeah. The world of outsider physics versus the current landscape of theoretical physics within academia. Because mainstream physics hasn't exactly been standing still, has it?
Not at all. And today, there's this massive emphasis on what you might call the cosmological frontier.
The really big questions.
The biggest. The origin and ultimate fate of the universe. The deep mysteries of dark matter and dark energy.
The stuff that makes up 95% of the universe, but we don't know what it is.
Right. Plus, the tantalizing possibilities of time travel, the existence of extra dimensions, and the completely mind-bending concept of the multiverse.
Yeah, these are the topics that really capture the public imagination now and dominate media coverage of physics.
They really do. And mainstream theoretical physics has ventured into some incredibly abstract, conceptually challenging territory to tackle these questions.
String theory being a prime example.
Definitely. The idea that fundamental entities aren't point particles, but tiny vibrating strings.
Vibrating in 10 or 11 dimensions of space-time, depending on the version.
Right. With these extra spatial dimensions curled up incredibly small so we don't perceive them in everyday life. It's an amazing mathematical structure.
It is. And then there's the multiverse hypothesis that often comes out of string theory discussions.
The idea that our universe is just one of countless others.
Essentially, yeah. The string landscape idea suggests there might be a vast number, maybe 10 to the 500, or even more of different possible ways for those extra dimensions to be curled up.
And each way corresponds to different fundamental constants, different laws of physics.
Exactly. And the multiverse hypothesis proposes that maybe all of these possibilities are realized. Each one represents a real, physically existing universe in a grander multiverse.
Our universe just happens to be one where the conditions were right for stars, galaxies, and us to form.
That's the anthropic reasoning that sometimes accompanies it. We find ourselves in a universe compatible with our existence.
It's mind-boggling stuff, and it's not entirely unprecedented, this idea of extra dimensions.
No, there was Kaluza-Klein theory back in the early 20th century.
Right, trying to unify gravity and electromagnetism by adding a fifth dimension.
Didn't quite work out as planned, but the idea of using extra dimensions persisted.
And now you have related concepts in modern cosmology, like brain cosmology.
Brain worlds, explain that again.
The idea is that our entire observable three-dimensional universe might be confined to a membrane, a brain, embedded within a higher dimensional space called the bulk.
So we're living on a sheet of paper in a larger room, metaphorically speaking.
Kind of, and there could be other brains, other universes, potentially floating nearby in this higher dimensional bulk.
Could we ever detect that?
Well, some theories suggest that gravity might be able to leak between brains, or that high-energy particle collisions, like at the Large Hadron Collider, LHC, might create tiny black holes or other phenomena that provide indirect evidence for these extra dimensions.
So scientists are actually looking for signs of extra dimensions at the LHC.
They are. It's part of the experimental program. Searching for deviations from the standard model that might hint at new physics, including extra dimensions or supersymmetry.
Okay, so when you step back and look at string theory, multiverses, brain worlds, coming from the mainstream, what's particularly striking is the significant role that imaginative construction plays, not just for the outsiders, but here too.
How do you mean?
Well, while these mainstream theories are typically built on very sophisticated mathematical frameworks, and they do try to connect with existing experimental data where possible,
Right.
they often end up positing entities and phenomena, extra dimensions, entire other universes that are incredibly far beyond our current ability to directly observe or test, maybe forever beyond.
So are you saying there's a making things up aspect to both?
That's putting it bluntly, but it raises a profound question, doesn't it? In this deep pursuit of fundamental knowledge about the origins and nature of reality, where exactly does the line lie between groundbreaking, mathematically informed, imaginative insight and purely speculative fiction?
That's a tough line to draw sometimes, especially at the frontiers. When does a beautiful mathematical idea become accepted physics?
Exactly. It's a question philosophers of science grapple with constantly.
Mm.
And it makes the landscape of both outsider and mainstream theoretical physics look maybe surprisingly similar in some respects. Both involve constructing elaborate narratives about reality.
That's a really interesting point. The tools are different, maybe advanced math versus mechanical intuition, but the act of imaginative world building might be common.
Perhaps.
And speaking of building things, let's circle back to Jim Carter one last time with a rather poignant image.
Okay.
For years, alongside developing his physics, he dedicated himself to planting redwood trees. Lots of them.
Redwood trees. Where?
On his property there in the Green River Gorge area, he planted them in clear-cut areas along roadsides and even formed a small, deliberate ring of redwood trees near his house.
A living ring of redwoods. Why?
It seems it was just this long-term, maybe unneeded project, something driven by an inner desire, what Margaret Wertheim, the author of Physics on the Fringe, eloquently calls a creative surfeit, an overflow of creative energy.
Wow. Planting redwoods, which takes centuries to mature. That's a long-term vision.
Isn't it? And that act, planting those trees, especially the ring, it becomes this powerful, evocative metaphor for Carter's life and his whole intellectual project.
That's so.
It represents this kind of organic expression of excess, a dedication to a long-term vision that goes way beyond immediate practicalities or conventional expectations.
It's like his physics.
Exactly. Just as those trees grow slowly, developing over time in potentially unexpected ways, following their own natural course. So, too, did Carter's intellectual journey take him down these unique, unconventional paths, pursuing possibilities outside the expected order.
Leaving this distinctive living mark on the landscape, both literally with the trees and figuratively with his ideas. That's a beautiful way to think about it.
I thought so, too. So, as we bring this deep dive to a close, what are our key takeaways here? We've journeyed through this incredibly diverse, passionately held world of outsider physics.
Definitely diverse. We met the singular visions of individuals like Jim Carter with his Circlons,
Walter Murch applying Bode's law everywhere,
Roto and his ether donut universe.
We got some historical context through Augustus De Morgan's fascination with his 19th century paradoxers. And we even touched upon these surprisingly imaginative, sometimes equally untestable frontiers of mainstream theoretical physics today. String theory, multiverses.
And it's important to reiterate, I think, that while these outsider theories might not align with the current scientific consensus, engaging with them, understanding them, still provides really valuable insights.
Insights into what?
Into the sheer human desire to understand the universe, for one. It prompts us to consider the very nature of scientific inquiry itself. What counts as science? What's the role of intuition, of mechanism, of mathematics, of imagination?
Yeah, and the multitude of ways individuals try to make sense of the cosmos around us. It's not just one single path.
Not at all.
Absolutely.
Right.
And if this mind-expanding exploration has sparked your curiosity, and honestly, how could it not?
Right. It's pretty wild stuff.
We wholeheartedly encourage you to delve further. Look into these fascinating topics, these individuals we've discussed. There's a whole universe of alternative ideas out there just waiting to be explored.
Which leads to maybe a final thought-provoking question to leave folks with.
Okay, hit me.
Does the sheer abundance of theories we see today, both from the outsiders and within the mainstream, with things like the multiverse theories that are pushing the boundaries of what we can even imagine, let alone test, does this proliferation signal some kind of fundamental shift?
A shift in how we approach knowledge.
Yeah, or how we approach the universe itself. Is the power of human imagination constructing these grand narratives becoming an increasingly crucial, maybe even central element in our quest for ultimate comprehension?
Wow. Is imagination taking over where observation perhaps can't reach, at least for now? That is definitely food for thought.
Something to mull over.
Indeed. And hey, if you found this deep dive into the fringes of physics as captivating and mind-bending as we did,
Hope you did.
please do us a huge favor, hit that like button, and definitely subscribe for more explorations into the surprising corners of knowledge.
It really helps us keep bringing you these deep dives.
Absolutely. You never know where our next exploration will take us.